Modern civilization runs on data we cannot see. While billions of phones and computers exchange information through invisible ripples in the air, there is no physical trace to mark their path. In the mid-1800s, this landscape would have been inconceivable. Scientists then viewed electricity, magnetism, and light as three distinct phenomena, each governed by its own isolated set of physical laws. Our ability to broadcast signals across this cityscape didn't come from trial-and-error tinkering with magnets or lenses. It began when James Clerk Maxwell developed a mathematical framework that linked electricity and magnetism directly, suggesting they were two parts of the same force. To understand our wireless world, we have to trace how those abstract equations physically became the hardware that moves information through space. Maxwell shifted physics away from the idea that forces simply jump across empty space. He proposed that space itself is filled with continuous electromagnetic fields, but his initial mathematical approach was inconsistent. The existing rules for magnetism worked for steady currents, but failed to account for non-steady systems, like a charging capacitor. To bridge the physical gap between a capacitor's plates, Maxwell introduced the displacement current. It wasn't a flow of electrons, but a mathematical term representing a time-varying electric field. Adding this term revealed a wave equation with a fixed velocity of 299,800 kilometers per second. Because this velocity was nearly identical to the measured speed of light, Maxwell realized that light itself was a form of electromagnetic radiation. At first, the theory was nearly unusable for engineering. Maxwell's original formulation involved 20 simultaneous equations with 20 variables, making it a dense mathematical curiosity. Oliver Heaviside, a self-taught telegrapher, simplified the system. He discarded the abstract potentials Maxwell used and focused purely on measurable electric and magnetic fields. Using vector calculus, Heaviside collapsed those 20 variables into the 4 concise vector equations that remain the standard for electromagnetic engineering. But mathematical elegance always requires physical proof. In 1887, German physicist Heinrich Hertz set out to generate and detect these waves in a laboratory. Hertz built a spark gap transmitter to accelerate electrical charges, using an unpowered wire loop as a detector. When the transmitter sparked, a corresponding spark jumped across the loop's gap. The invisible wave crossed the room, proving Maxwell's wave theory was a physical reality. Hertz considered this a purely academic victory. He famously claimed his discovery of these Hertzian waves had no practical application. Guglielmo Marconi saw the potential Hertz ignored. He realized these waves could carry telegraphic signals through space without any physical connection. Marconi's breakthrough was an engineering shift. He modified Hertz's horizontal antenna into a vertical monopole. By grounding the antenna, Marconi enabled the radio waves to hug the planet's surface and travel over the horizon, rather than moving straight into space. In 1901, he successfully transmitted the Morse code letter S from Cornwall to Newfoundland, over 2,000 miles across the Atlantic. This single transmission proved that wireless signals could span oceans, marking the transition from theoretical physics to a global communication network. Marconi's radio waves were just a sliver of the full electromagnetic spectrum, which extends from extremely long wavelengths to those smaller than an atom. Today, we manage this spectrum like physical territory. Organizations like the International Telecommunication Union assign specific bands to prevent signals from interfering with each other. At the low end are extremely low frequencies, or ELF. These massive waves can penetrate deep into the ocean, allowing for communication with submerged submarines. Moving higher, the waves tighten into the ultra-high frequencies we use for Wi-Fi, and the millimeter-scale extremely high frequencies that power 5G cellular networks. Even visible light is simply a specific frequency band on this same continuous scale, sandwiched between infrared and ultraviolet. Our wireless technology is the direct result of a century-long translation. It began as a set of mathematical proofs for unified fields and evolved into the infrastructure that now maps the entire electromagnetic spectrum.